So we still have half an. I think it's at 1 o'clock. We will have the break. Yeah. Okay. So let's begin the first part for interactive session 2, and we will continue after the lunch. So a little bit, interactive session 2 will be about P4. Okay. So before we begin, I would like to present to you a quick P4 tutorial. So let's open first of all the here in Hackfest 3 we have P4, and here we should have this main.p4 file. This is the source code for the P4 program we are using until now. And a P4 program consists of basically four main things. We have in the beginning a definition of the various headers we will use in the program. Then we have a parser that describes how these headers are parsed. Then we have, I will go back, I just want to give you the overall impression. Then we have this control block, as we say it, which describes the various actions and tables that can be done. And finally, we have the deparser, which describes how we can then emit this packet in the wire. So basically, these are the four blocks of a P4 program. So for example, here we have a header. Basically, this is the header of Ethernet. What that describes to us is that an Ethernet header consists of three values. The first 48 bits are the destination address, so the MAC address. The next 48 bit are source address, and the final 16 bit are the ether type. It is important to note that here that there is a sequence. We begin with the first, and then we follow with the second. It's not the same if we have put ether type in the beginning, for example. Okay? So that is one thing to take into account when defining the header. For most protocols that we use in IP, these header files can be extracted from RFCs or even from Wikipedia for most of them. Then we have this parser. Basically, a parser in P4 is a state machine. It always begins in that state start, and it always ends in that accept state. What we describe here is how we, when a packet comes, how we extract the various headers from it. So here, for example, we have in the packet in packet, and we say that, first of all, extract the Ethernet headers, and then based on ether type, so based on that field there, if it is 0x800, which corresponds to the IPv4 code, then transition to parse IPv4. Okay? And then in parse IPv4, we extract the IP header. It's not defined here, but we will see about it. And then we say that we accept it. This is how we define a header, and then how we define a parser. The control block, basically, as Giorgos said before, we define the various tables that we can have. So a table mainly consists of a set of keys and a set of actions. The keys are there to show us how we will match this table, and the actions are there to show us what can be done, what will be done in this, if this hits or if this matches. So in that case, for example, we have a layer 2 exact table. We match based on the destination address by exact. We could have other stuff here. For example, we could have longest prefix, or we could have some masks, etc. And then we say that for this table that has this key, we can have two actions, either set egress port or drop. And we also say that the default action is drop. So if we then go on our control plane and do not define any match action here, this will default to drop. So everything will match and will go to drop. And then we can define the various actions that we use here. Actions can be thought of like functions in other programming languages. So basically they have a name, and then they have some parameters, and they have a body. The parameters are, in most cases, they are set by the controller. So for example, here we have this action which says set egress port. It has a parameter that takes a port number. And what it does is that in standard metadata, it enters in egress spec this port number. This standard metadata is really important in P4. It is defined in the P4 specification. However, it is also dependent, some of them are dependent on the specific switch we are running. So, for example, if you are running some ASIC like Barefoot Toffin or something like that, some hardware switch, it could have different standard metadata. Basically, there is a subset that is always the same, but there is a superset that is not always the same. This specific one, the egress spec, defines where the packet should go out of, which port should go out of. So this was also shown, I think, by Yorgos yesterday. This defines the V1 model that we are using in our case. And basically, as I've said before, we have a parser that parses the packet. Then we have different match action pipeline tables. And then we have a deparser. So, first of all, let's take a look at our P4 program. Yes. To see all this that we have described. So this is the main P4. Basically, what we have here is a really simple header definition and parser. We are only defining the Ethernet header, so MAC address destination, MAC destination address and MAC source address, and the Ether type. And then we define a structure that is the parsed header, so what will be eventually parsed, which is just this. If we also had, for example, header IP here, we could say that the eventual possible parsed headers could also be here, IP, for example. Why this is useful because later when you use control blocks, it's easy to define different cases for parsed header. For example, if this is a bit simple, but if we had also UDP and TCP, we could have two different parsed sets, one that is TCP, one that's UDP, and then we have some specific control blocks for the one and some specific control blocks for the other. So it is good to also have these, let's say, intermediate headers. And then, okay, we have this local metadata. This is some stuff that we could also use for ourselves. Then, as we showed before, pretty much the same, the parser. And the ingress pipeline, we have also this set multicast group, which is how we could have multicast. We didn't showcase it, and we won't go over this, but we could also, this is the way that we could also have multicast groups. But basically, we have the drop action and the set egress port action. And then we define this L2 exact table, which has, as we showed before, as a key the ingress port, so where the packet came from, and it can you can actually set the egress port, so where it will go out. And the way we do that is we use this apply block, which says apply this table to the packets, to the incoming packets. Then in the parser we usually emit the packet as we want it to be in the wire. So usually, if we are talking about IP networks, it's Ethernet, then IP, all the encapsulation. Okay, so this is the P4 program we were using until now. The idea for this session, and most of it will be after the dinner, is to try and insert some in-band telemetry here. What is in-band telemetry? We have a session after that, probably by Yorgos, who will present the in-band telemetry in more detail. But the general idea is that how we can, for example, now, previously, we built monitors that were running end-to-end. So we couldn't know all the intermediate steps, what's happening. In-band telemetry is that idea, how we can have information from all the intermediate steps. So we know, for example, the time it took from one switch to the other, or we know how much time it took in the queue inside the switch, etc. So we are providing a simple in-band telemetry. Well, it's not in-band telemetry. I will explain why. But we're providing a primitive, let's say, step towards in-band telemetry. And for that, we were using the IPv4 options header. This is an optional part in the IPv4 protocol that nowadays it's rarely used. It used to be that you could import their information about the hops, the intermediate hops, or some security information that with IP secure it's not relevant anymore. And we're going to basically use that to embed some information from the switches. So what kind of information can we embed in the switches? These are some, there are more, but these are some of the standard metadata that usually switches have. So we have, as we saw before, ingress port and egress port. We have the packet length, so the total length of the packet. The ingress global timestamp and egress global timestamp. So basically what that means is that when it came and when it goes out, this is in Unix epoch format. We have the multicast group if it is multicasted. So when you multicast a packet, you assign it to a multicast group, which means that it goes to some specific, out of some specific ports. So ports can be in groups, so that doesn't, multicast does not mean flat, does not mean out of every port. And then we have these things that have to do with the queue in the switch. So basically, the timestamp of enqueuing, the depth, the queue depth at the point of enqueuing, and again the timestamp at dequeuing, and the queue depth at dequeuing. What? I think this is. Yes. I think that also there is a time delta that supports exactly what you're saying. Okay. So to see that, we will see it later, but we have to have some programs. Why is that what I'm showing you not in-band telemetry? Because the general architecture of in-band telemetry has this notion of egress and ingress switches. What that means is that the hosts do not see the telemetry. So a host sends a packet into the network, and the first switch it goes through, it is the ingress switch, and it begins the network, the in-band telemetry idea. And the last switch before the host is the egress. So the first switch creates this all the header needed for in-band telemetry, and the last switch removes them, so the host does not see it. In our case, we are not doing that because it is a little more tricky to do that. But we are we plan to support it in the future. What we are doing is using, having the information on the host. So we have on the client, we will have a program, the sender, that will create this IPv4 option packet. And then as it goes to the switches, it will be populated. And on the receiver side, we will take the result. This is different. The scripts are taken from the ETH Zurich. This is a really nice, if someone is interested in before, this is a really nice GitHub. I suggest to look at it. It has many examples and many exercises and also presentations. So, okay. So, the program, the P4 program we will use is here in Hackfest 3 int. Int is in-band telemetry. The Q depth int basic. The basic, this program basically marks the Q depth when the packet was taken, okay? So let's see how that is defined here. First of all, okay, we have some constant definition here that are defining basically that this value will be this value. So we have some more expressive language, don't care about it. Then we also define some types. So instead of writing all this, you are writing this. So basically we're saying that a MAC address is 48-bit and an IP4 address is 32-bit. And then we're going on to define the headers. So we define, as before, the Ethernet header and also the IPv4 header. You see that we should follow the RFC for all the various fields that exist. And then we also have the options. Again, these are standard, the standard option, IPv4 option structure. Then, in the int header, which is the part that we care about, we have these three things. So basically, we have the ID of the switch, we have the Q depth, and we have the output port. So at the end, using this program, we should know which switches it passed through, the Q depth when enqueued, and the output port where it went out. Of course, this could, I mean, this particular is more to show you that we can do this, because the output port and the switch ID, we already know them from the way we structure our services. The Q depth, we don't know it, but because we don't have a lot of traffic, it usually will be 0 or near 0. But we will see, maybe we can have timestamp later and see how we can use that. Then we have some metadata, and you can see the packet that we're using here is comprised of Ethernet, IPv4, IPv4 option, the count, the number of options we can have, and then this list of int headers. Okay? Is this understood until now? Okay. Again, the same follows for the parser. So we begin from the start. We extract the Ethernet type, and then we, based on the type, we parse IPv4, or maybe we could also parse something else. In this case, we parse IPv4. Here we are doing some verifications regarding the options, because this IHL field, if we have options, it usually, if we don't have options, it usually is set to 5. Okay, so if it is not 5, then we can parse the options, and we go on. Then we have this L2 exact table, which is the one that we used before, so nothing new here. But on the egress pipeline now, so here, until now we only used this one. Now we're talking about this one. So after the packet went through the switch and it is ready to leave the switch. So in that pipeline, we do some things that we are able to, so that we are able to have the int. First of all, we add the int header. This, as you can see here, we create the header we defined before. So we say that it is valid, and then we set a switch ID, which is taken as a parameter. This is an action, okay? And then we use the standard metadata. So to get the egress port and get the queue depth. You can see that there are some casts here. The reason that why is that is because we are constrained by IPv4 options. IPv4 options have specific, let's say, bits that we can actually use. So as we showed here, queue depth, for example, is 19 bits, but we don't have that much space, so we should make it smaller. This is why IPv4 is constrained. Okay. Eventually, when we want to have full in-band telemetry, we want to have to define our own protocol so that we are not constrained by any of these options. Actually, if somebody goes over the in-band telemetry specification, one could see many different options, either using the IPv4 options or some options from TCP, or even defining your own protocol. There are some examples there. Then, Then we update the IP header length so that we know IPv4 has in its header, it has the length of the packet. As we have added more values, more bits, this has lengthened. So we have to update this. And then we define the int table. Here, as it is, first of all, considering what I've showed you previously, there are two differences. First of all, there are no keys. And second of all, this default action is also has a parameter. What this means, what this table does, is that it always matches. And by default, it calls this add int header with the parameter of 1. So if we will run, and we will run it late after the break, this P4 program, we will see that the packet will go through the switches, but it will have switch ID 1 everywhere. Because by default, it goes 1. And we don't have, we haven't implemented any P4 services that actually manipulate this table. And then on the, okay, we have to also update the checksum because we did a lot of changes in the packet. In the previously, we didn't care about checksum because we take it as it is. We just change where it goes. Here we are changing the packet itself, and then we are deparsing it together with the int headers. So this is the P4 program we will check when we come back. Are there any questions until now on the structure, on how it is and stuff? Okay. Okay. The idea is, first of all, to check the program itself, see how it works, then to see how we can change this part here in order to have a key, and then also in Teraflow create the service to put the correct switch ID there. Okay? And then the third part is, as I've said before, here we are having the queue depth. This is because we have low traffic, it will be 0. Okay, so we will check to see if we can change this to something more relevant, for example, timestamp. Okay, this we will do after the break. I think we can break now and resume later. Okay, so Now we are going to go over the compilation of P4. Again, for that we are going to use the NGSDN tutorial, which has an easy command that compiles the program. However, it needs to find the program in a specific place, etc., etc. So instead of that, I have created this build P4 script. So let's first cd here, and here you should get build P4, and then this P4 program. Yes? Hmm? Are we in the same page now? Okay. So if we run now this build P4, it is basically this command, and we give it this program, it will build the program and also copy the artifact, the compiled, this, I think, yeah, these two P4 info and P4 binary to the correct place. And the, sorry? Yeah. You should get this result. If you get something else, tell me. Yeah. Okay. So now, if we go one directory behind and then in P4, we should have here. This is backup one, which has been created now, and it is what we had before here. And then we have this JSON and this P4 info. Basically, what is described here: the P4 bin and the P4 info. The JSON, it's not really relevant now because it has some specific information for the BMV2. So let's not see it. But it will be interesting to see this P4 info first. So let me open it here. P4 info. Okay. So this P4 info contains all the various tables that exist in our program, together with the keys, the match fields that we can match on, and also the various actions as references. It does not describe what they do, it just describes that they exist. So for example, we can see that there is a table called L2 exact that has match fields, the ingress port, and it can do these actions, these two actions that are referenced below. And also, just to make sure that we have the correct P4 info, you should have also this table here, which is the egress pipe symbol int table. Is this correct for everyone? If you need to find the file, again, it's under src tests hackfest 3 P4 info. What? You should have this table. This is what you're saying? I couldn't hear it. This one? Okay. Okay, great. And then check that in that path here, controllers RC tests hackfest 3 P4, you have this P4 info. The second table should be egress pipe implement. Great. Okay, so we have this P4 info. Now, We are using this script here, this setup script. What that does is basically copying. Let me open it. Setup. Basically, it copies the things that we have under P4, so the info and the BMV2 JSON. It copies them to the appropriate component. In our case, the device. As it is now, and this is also a bug we found during the preparation of this Hackfest, device, if it connects to the same device, SBI basically, if it connects to the same device twice, it uses the old configuration. So before doing that, let's go and redeploy TerraFlow. Make sure that in your my deploy you will have this skip build as yes, so that it doesn't take much time. The best way to do that is just git restore my deploy. This will be the one we want. So if that is complete, then we can source it and we can start the deployment. So let's just wait a couple of minutes for the deployment to complete, and we will continue. Basically, we are running now the commands from line 93 in the commands.txt. First one, we cd on the int directory, and then let's first run the first one, copy int helpers. Okay? Okay. Then we connect to Mininet again, and then run this install Scapy. What we are doing now with this is that we are installing Scapy, which is a really interesting Python library that can create and receive and parse packets. And we will be using it so that, as we said before, to create the packet with the correct IPv4 options, and then receive it at the other end and make sure that we get the response. So did the deployment... when you installed Scapy? Give me a minute. Did anyone else have the same permission problem? If you pulled... No, sorry. First you... sorry. Yes. First you connect to Mininet. Okay. And then you install Scapy. So, are we all done with this part, with the installation of Scapy? You're still waiting. Okay. So cd in the controller and run the setup script in the other terminal. Then bootstrap and create service. Sorry? Run on the setup screen, bootstrap and create service. Not inside Mininet, in another terminal. Yeah. Yes. Are you, where are you? It's okay, don't worry. They did installed? Did it finish install?
Yes, yes, it finished. That was in the other.
What?
That was in the other terminal.
Yeah, but this one should work. Minus here. A. My gosh, you have to redeploy.
What's happening?
For some reason, the device service did not come up.
I have to read it.
Yeah. Okay, just source and source my deployment. Source my deployment and deploy. Okay, have you finished upgrading the SCAPI? I think it's. Have you finished the upgrade? Okay, okay. So now, for everyone that has a running TerraFlow, we have just run the three commands: setup, bootstrap, and create service. Okay, we're in this place. And in Mininet, we have installed SCAPI. These are the place we are now. So now, let's open another terminal. You can follow the commands. It's from line 99 in the command section. cd to the ng-sdn tutorial. Make mn CLI, which will give us the CLI of Mininet. Okay. Okay. Now, Now the problem with Mininet that we're using that framework from ng-sdn is that it is not easy. I actually haven't found a way to have open multiple Mininet CLIs. So to solve this, because we need to run a script both for client and service, we're going to use screen. But because this part here, the Mininet CLI is not a real CLI, so it does not, it has bus, it does not sources or bus RC, etc. When we start a screen, we will have to be a little careful because it does not register things like backspace. So if we did something wrong, backspace will just print the character. Okay? So for anyone that does not know what screen is, it is a software where we can have multiple sessions running in the same terminal. So first of all, run this, which is server screen -s and some name here, let's say rec. What this does is that it creates a session that's called rec in this case. And then here, we just want to run this. It should say that. Because you don't have the deployment, you have to wait. Maybe you should go and... Sorry, what? Make a mini CLI, you mean? This one? Okay. Yes. Yes. And this, where it says mn, it is inside Mininet prompt. And it says that in the server namespace, run a screen -s, etc. Mohammed, is it done? Okay, then run the first 3 steps: setup, bootstrap, and create service. It's in the commands here: setup, bootstrap, create service. Okay, so do we have this, the result here? It's dying. So now, to leave screen, we just need to press 3 keys: Control plus A together, and then D. It says also in the command file. The Control A together, and then D. Okay? We're like this. You press Control D maybe. Run again. Make. Wait. Okay. So copy. Control A and then D. Oh no. So, did you understand what happened now? Because it is a little not transparent what has happened. So with screen we created a second session. We then there ran the receiver script, and then with Control A and D we went back to the original session. Okay? So in the background the receiver runs, and now we can try and run our Python script. Are we all okay with the? Okay. Yeah. It is a little, but I couldn't find a way to do it better. Yeah, it's not the screen that is the problem. The problem is that because we're inside Mininet, it does not create a prompt. It does not. Yeah, but unfortunately, I couldn't find a way to make it more friendly. So if we run this, we should get something like this. So make sure that we're all on the same page and that we have run this command here. Yes? The rest? Okay. Have you guys? Now we send the packet from client to the server. And this is, it prints us the packet that we have sent. And as you can see here, it has all the Ethernet, IP stuff, etc. And it also has this int header. Okay? So, are we all here in the same screen? No? You need some help? Okay, wait. So we have sent the packet, and now we want to see the packet. What we do for that is basically, instead of doing this as we did before, we do -R. We cannot scroll here, unfortunately, so don't try it. But we can see that it has entered some information here. What has entered is that this passed through various switches. As we have showed before dinner, all the switches had ID of 1, but it captured which port it went through. So that shows, first of all, that our program works. It is not a correct program because, first of all, every switch ID is 1, and also the queue depth is not really information that we can use, but it shows that our program works. Is that understood? This one. So is it understood what we tried to do and what we showed? Okay. I will come. Just give me. So now, first of all, enter here and just press Control and C, and then exit. Okay, so that we close this receiver. And now we want to see the P4 program. We want to see how we can change it to actually have the correct ID, first of all. Okay? So let's go over to our P4 program here. It is under int. This is the P4 program. Okay? And I want you to check what we do here in the L2 exact table and try to do something like that for this table here. So this table does not have any keys. And what we want is, instead of having this default action here, maybe we could do this like no action, okay? But we want here to be able to have keys like the one above, so that we are able to set the add-int header by the controller. Is it understood what we're trying? Or should I go again, because maybe I said it. So as it is now, by default, it will enter add-int header 1, which corresponds to this action. So for all switches, by default, it will be switch ID 1. And because it has no keys here, it is not possible for the controller to actually send some command and say that for that kind of package, do that. And in do that, we will also set the correct switch ID. So based on the table that we have above here, I want you to try and change this table so it doesn't have as default action this add-int header 1, but it has some key that we can use from the control plane. I'll give you some minutes and we'll discuss it. We already have the our headers. So what we want now is, okay, let's go over this again. As it is this table now, first of all, compared to what we have seen, for example, here, let's go over this table first. Okay, it's too far. So this table says that we have this kind of keys and this kind of actions. Okay, so the controller can come and say, when something comes from port 1, for example, you will set egress port, and it can also set this here, the port here. So the controller uses keys, action, and the parameters of actions. As it is here, first of all, there are no keys. So the controller cannot say, when this happens, do this. It can also, it can only use the default action. Yes, first of all, we should add a key. So what we want here is to be able, first of all, to have a key so that the controller can say something about it. And then we will see in the controller how we will call this correctly. So yes, the answer to that is just add a key. And this can be seen in the solution, basically. So the change here is that we have added the same key as before. And we have changed the default action to no action in order to not have any conflicts with which, normally, if there is a rule, the default action is disregarded. But just to be sure, we change the default action to no action. Yes? No. As the key, we use this, which is the ingress port. Basically, what port the packet came in. This P4 operates on the switch. It doesn't know anything about different switches. It is just a switch. Okay. We could do that, but I mean, it's a little complicated. If we wanted to build something like that, it is a valid case. So we could, instead of having here standard metadata ingress port, we could go and check this here, the int headers, for example, the last int header, so where it came from, and check the switch ID. That's what we are saying, right? Yes, we could do that, but now we don't want such a thing. Okay, so in here, controller SRC tests Hackfest 3 int solution, there is this program. Okay? Now, we're going to go over a little bit the P4 service handler. So we're going to go over how Teraflow uses services to configure the devices. Okay? So I want you first to open in here SRC and go to service. Okay? Almost all the components of Teraflow have this structure where we have a client and then a service. Okay? The client is the one that we have used to be able to communicate with the component. The service actually has the business logic of this component. The service and device are really similar in the sense that they have a certain API that they implement, and then they have what we call plugins or drivers, or in the case of devices, or in the case of service, what we call service handlers. Basically, what these are specific parts of the program that implement this standard API, this interface. Okay? So if we're talking about in object-oriented terms, for example, the service handler API is an abstract interface, and we're describing a class that implements this interface. And by that, we can have a simple interface from the service and implement a specific part, for example, in our case, for P4. Okay? So under service handlers, there are many different service handlers. So there is one for layer 2 using emulated devices, one layer 2 VPN using ITFL, one for OpenConfig, etc. We want to see a little bit about the P4 service handler. So open this one, this file. Okay? So first we're going to go over how this service handler works here, and then we will try to alter it in order to accommodate what we have changed in our program, in order to accommodate our basic int. So, yes? Of course. Mm-hmm. Yes. This is what Yorgos described yesterday, that we have different levels of abstractions. So basically, let's say here, for example. The SBI is able to communicate with the various devices. Okay? So in the end, it's the SBI which will send the final the final rules that will be implemented. However, we have this service layer that basically takes a more abstract concept, which is an end-to-end layer connection in this case, or it could be, as if we evolve it more, it could be, for example, some access control list here. So a service and also some access control. And what that does is that here, in what we're seeing, it's using path computation, but it could also use some other component. And what it does is that from this high-level abstraction, it translates to specific rules that then are sent to the device, to the SBI, to being... Yes, yes, yes. So basically, if we are going to see now this P4 service handler and go to here, set endpoint, line 105. Again, to understand what this does, we can read the code. Also, we can go to the service protobufs and see what that does. Basically, what it does, it also has nice comments. It creates or updates a service based on a list of endpoints. So, as an input here, it would take the two yellow ports, the endpoints of the service, and it should result in some specific configuration to the SBI to be configured in the switches. So let's go over a little bit how it does that in our case. Again, I want to remind you that this was built for the program we saw earlier, not the one for the telemetry, which it had only one table that matched in which port it came and instructed to which port it will go out. Okay? So what that does is basically yes, I said to you something wrong. This set endpoint comes a little later. It doesn't take just this endpoint and this endpoint. Actually, this set endpoint takes all the endpoints that were computed by path computation. Okay? So we're seeing a second layer. If we were to go through all the service handler, it will first hit the service to request a service from here to here. Then the service would request from path computation a path, basically. And from path computation, the set endpoint that we're now looking into will be called. Okay? So in the set endpoint here, we have a list of all the endpoints that will be configured. In other terms, if we look here in the web UI, it will take this. So basically, switch 1 endpoint 3, switch 1 endpoint 1, switch 2 endpoint 1, and it goes on. And then, for each endpoint there, okay, basically, it tries to see if those two endpoints belong to the same device, and if they do, and when they do, basically, because there will always be two endpoints in the same device, because it has to go through. When they do, it says, okay, this endpoint A and this endpoint B, and then it calls this create rule set from A to B and from B to A. Okay? And now, if we go a little above, it shows this create rule set here. What does that do? Basically, it creates a configuration, a rule, okay, for the P4. So this eventually is sent to the device that concerns the table named L2 access table, exact table, sorry, matches on egress port based on the endpoint A, and sets the egress ports for endpoint B. Is this idea clear? Yes. Yes, I can elaborate. Okay, so we have. Okay, can you? Is this readable? Okay. So we have this set endpoint. Set endpoint takes a list that contains endpoint of devices, and this list basically describes the path we want the service to have. So this list here, the input of this function is this list here. Okay? The endpoints we have for this service. Not the endpoints of the service, the endpoints we have for the path of the service. Understood? So in this case, it doesn't take just these two, but it takes this, and this. All the path. Okay? Then it iterates over them and tries to find in that list which endpoints are of the same switch. Why we want that? Because we can enter rules on the device level. So the device knows only about its own ports. Okay? So it iterates through them, and when it finds two endpoints that belong to the same switch, it goes and creates these rules from one point to the other and from the other point to the one. Until now, is this clear, what we're describing? Any questions, or I can elaborate more if you want. Yes, yes. That's why you have. That's why you have two calls here, from A to B and from B to A. This is a function we'll go now. So it creates this rule and appends them to the config rules of the device, and then creates this rule, appends them, and then it sends to the device the configuration. So configure the switches like this, okay? And in the create rule set, so create rule set takes two endpoints, and it creates a rule, a P4 rule, P4 runtime rule, to create a connection between them. So it uses the program we were seeing before, the main.p4 that we had, and it uses the L2 exact table with key the first endpoint and with parameter the second endpoint. So this rule here creates a connection, a forwarding rule, basically, from one port to the other. And we do that for all the switches in the path and for the back. Okay? Is this clear? Yes, when we say here endpoint A and endpoint B, also it has the name endpoint A, endpoint B, but here it has endpoint B and it is switched. Yeah, it's parameter. Don't mix the variable with the parameter. Okay? Is this understood? Okay. So, what I want you now to do is create the rule for the int. Okay? How should we do that? First of all, we should come here and let's copy this function. And instead of rule set, let's say that it is create int set. Now what we want to do now is that extend the service handler in order to accommodate the second table that we have, this one, the int table. As it is now, the before service handler accommodates the L2 exact table. Okay? So it accommodates this one. We want also to accommodate this one. Okay? So what I would suggest is begin with creating this. So copying the create rule set, renaming to create int set or something like that, and then try to change these parameters. So the table name should be different, the match field should be different, and the action name should also be different. I would say take a moment to try and do that, and we will come back and see. As a hint, this name and parameter, this things that we should change can be found in the P4 info. But to begin with, just put what you can understand from here. We will later see how we can check the P4 info for that. So let's take a moment about that. Yes, I see that most of you have written something. Let's go over how we can find these names here. The first idea is to go here to the P4 program and try and use these here, these names here, right? What? Yeah. The thing is that similarly to what we said before about the protobufs, P4, as I've said before, from the program, it compiles a P4 info. So again, if we want to create rules, our real guide is more the P4 info and less the program itself. So let's open P4 info first. It is here, tests. It should be in here, in P4, P4 info. Okay? So we see that we have this table. So here in, where is it? In service handler, in the table name, we should put this table. What is the difference from what we see in before? Basically here it says int table, just int table. In here it says egress pipeline impl. Basically this name dot this name. Okay? Then what else do we need? We need the, yes, sorry. Of course. When you mean alias, what do you? Ah, that's a good question. I'm not sure. I haven't even seen that there was an alias there. That's a good name, and we can test it. To tell you the truth, I'm pretty confident that if you don't include this, it will not work. But I have in my mind some experience that I put just this and it didn't work. But I'm not 100% sure that this would be. Okay? So in table name that. In match field, again, we are using basically the same because this here sorry. Ah, sorry. What we are seeing here is the P4 info for the one that was, okay, that was my mistake. We didn't build this one here. We will do it now, but in any case. So here we use the ingress port, and then for the action name, we would use egress blah 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 dot how is it said here? Add int header. Okay. Okay. Let me just open the solution for the time being, and we will. Yes. Where is it? So yes, this is the end. Here we have the standard metadata ingress port, and then here we have egress pipeline implementation dot add int header. And as you've said, we changed the endpoint to be ID. Okay. So because now what we are entering there, it's not an endpoint anymore. It is more the semantics of the stuff. We're not entering an endpoint, we're entering an ID there. We're setting an ID, not an endpoint anymore. in this addInt, in this int table, what we're doing is saying that this particular switch has this switch ID. Okay, so we don't want. We already have the rules on how to create the service that we were describing before. Now we just want to make sure that when a packet comes, it will have this switch ID put in the header. Yeah. Okay, now I think you can also copy that if you take the solution. And now it's pretty obvious how we can continue. We have this create rule delete now, because we also need that to delete the service. Okay? So what is the difference between delete and set? For Teraflow, it's just this little word here. Here it says delete. Here it says set. But inside the parameter of this function, it's exactly the same. You see? Okay, so hopefully most of us we have finished the deployment. Let me get out of here. Okay, so I've written there, do not run anything, because let's go back to where we stopped before deploying. So back to the P4 service handler. Now, don't open the one that is in the source folder, which is the solution one, but open the one that we copied, so the original one, okay? Let me see where I have put it. This is... Okay, so most probably this is something you should also have. So you should have some create rule set. This was originally there. We have created this create int set, which was what we described before, with correct here. I have just nothing. So the next step after, if we see, this is for the create service, okay? So for the set endpoint method. There is also, if we go a little down below, the delete endpoint. Basically, this is the inverse. So the set endpoint creates the service, the delete endpoint deletes the service. The structure is almost the same, with the only difference that here, instead of calling the create rule set, we're calling the create rule del. Okay? And this function, basically, if you look at it, it is the same as this one. The only difference here is that instead of saying JSON configure rule set, it says JSON configure rule delete. Okay? However, the content of this function is the same. Yeah? So what we want now is, just like we created this create int set, create also create int del. Okay? This is pretty simple. I mean, we have the int set. We just copy these two lines and insert here the correct parameters. Let me just take the parameter to show you better. Sorry, give me just a minute because I think by mistake I copied the wrong file. There's handlers before. Yes. So we have already, this is the solution. Okay, so we have already created sorry, what? Yes. This is it understand what I was saying? Yes? We have this creating set that calls JSON config rule set with this body, and we want also to have creating del, which calls JSON config rule delete with the same body. It's simple. The next point is to actually, so this is present in your file too, but we want to create a new rule, which will be with creating set, and pass the correct thing here. So the device ID, basically. Yes? So how can we find the device ID? Based on the fact that what we are getting here in this set endpoint function is a list of the of this basically. Yes, exactly that. So basically here we have this device. We are keeping here the name of the device. Basically, we are getting the device, all the device, based on the UUID of the device we have. Okay. So, for example, we have this path. Okay. We are calculating and finding the same street so that we can create this connection. That was what we were doing originally in the service handler. Okay. So we have basically the UUID of the device and the name of the device. So what we do here is that from this device, we get the, here, where is it? Here we get the name. Again, for this to be more understandable, it's best to go to the proto files. Okay, so if we open proto files and we go now to the device proto file, we can see that there is this context.device. So that leads us to go to the context proto file. And in the context proto file, we have this device object, which has all these things. Okay, so we have a list of endpoints, and each endpoint has in itself the UUID of the device. What we do is we get from the SBI component the whole device object based on this UUID, and from that we keep specifically the name. Here we call the get device with this particular device UUID. So this device here, this variable, contains such an object. Okay? This task executor here is like the one we used before, the context client or the monitoring client. Okay? So in this device here, in this variable, we have all these objects. And from that, we just need the name. And more importantly, because we want just the ID, we just want the last character of the string. Okay, so instead of SW1, we just want 1. Instead of SW2, we just want 2. And that is what we are doing here, actually, in line 200 in the solution, where we say endpoint A, and then the device name and the last character of the device name. Okay? This is in the solution. So here, we would pass this, and this would create this rule with ID here, just the last character of the name, which is actually the ID. Again, you have to understand that as service handler is written now, this presupposes that we name the switches in that way. If we have a different naming scheme, it will not work. Okay? This is a thing that we are trying to cover and find some ways maybe to make that more universal or general. And this is the problem that you may have when you are writing service handlers, that you're trying to describe something that is more abstract and more general, but at some point you have this to make it, to instantiate it, to make it for some specific reason. This equilibrium is a little difficult sometimes, to find this equilibrium and say, okay, what is abstract, what is specific. Of course, this is just an example for the Hackfest. If we have, and as we plan to do it in the future, to write a full in-band telemetry service handler, we are trying to disassociate this with the specific names and make it more universal and generic. Okay, so now we took a peek in the service handler, how the service handler for P4 more or less works. I hope that, okay, the specifics could be a little difficult to grasp, but the general idea, I think that, I hope that you have understood. Basically, we call this set endpoint with a specific path we want to take, and from there we start and build our rules. This is what the P4 service handler does. So now we have copied this in our regular source files, and we have deployed it by building it again. So we want to try and see if we have succeeded. First of all, before doing that, we have to make sure that we will copy the correct P4 files. Okay? So let me see if I have it in the commands section. Not really. Okay, so let's cd int solution. And there you can see that there is also this P4 program, which is the one that we did in the beginning of last hour, which was to create it basically this one, which has a specific key, etc. So first of all, we have to build that. Okay, so the build. Let me just check the build before to make sure. Build before. Okay, so just go here in the controller src tests hackfest 3 int, and now we will run the build script, but instead of giving it just this file, we will give it the solution qdepth int basic. Okay? This should give you the same result, that the P4 program has been compiled, and then this also copies the files in P4, so in controller src test hackfest 3 P4, And now this before info here should have should be the correct. So if we open it, which is before info, we should see here that egress in table. Now the egress pipe implementation int table has match fields. Before it didn't have, and the match field is standard metadata ingress port. This is line 35. Yes. When we run the build, this script basically does 2-3 things. First, it copies that P4 program that we're giving it to the correct directory. It builds it and then copies the artifacts here in the controller SRC test Hackfest 3 P4. And also creates backups. You can see backup 1, backup 2 from the previous files. So just make sure that this file here, in line 35, I think, yes, 35, it has this match fields version. Okay? Great. Now we can go to the controller directory, and we can run our routine, which is setup, bootstrap, etc., until create service. So setup. Setup basically copies the artifacts that were compiled to the device pod. Bootstrap, which registers devices. What? Okay, give me a minute. Wait. I'm coming to see. Cannot reproduction. Why does it not work? Should we see it later? Is it okay if we sit later and just sit there? Okay, sorry. So are we all here in the create service? Okay. Now comes the tricky part with the screen again. Okay, so we don't have to copy the receiver and the sender because we didn't recreate the Docker container. It still has them. It doesn't change anything. So we go to ngsdn, make mn CLI, and here we run this server screen -s rec. And here we run python receive.py. Make sure that you don't press tab. I know it's tempting. And Control A and then D. And we just use this to send the message. So we use client Python, send py, the IP address, test, this is irrelevant, and 1. And then if we see here, we see that we have this switch trace. It goes from switch 1 to switch 2 and then to switch 4. And that corresponds basically to that. Switch 1, switch 2, switch 4. So that means that what we wanted to do, we have actually done, and we have a way to push a certain rule that couples, let's say, the switch to a specific ID. So again, the information we get here is mostly redundant because we already know the path from here. But here we have a static path. If you had some routing done, so we do not know the exact path the packet will take, this will be very useful because we know that the path took this, the packet took this path also. And also, it's important to note that why this is called in-band telemetry is because we don't need some extra flow to do that. So basically, we're incorporating this information that is useful on the general flow that is happening. So here, okay, we're using this sender and receiver, but if this is done correctly, as we will see later in some slides, this will be done just by a user sending a request, for example, for a web service or something like that. This happens on the switches. And also, because this happens on the switches, first of all, it's much faster. Nobody else is involved but the switch. It happens as the packet traverses the switch. And it is much more accurate than what we could predict or what we could say. Okay? Any questions about that? Fighting with the screen. Okay. Now, I've said before that this is, we're now using basically QDepth, which is redundant information. I have here, I have shown you before, the various, where is it? Standard metadata that we could use. And I think that the next step is try and use some other metadata, so not QDepth, but for example, some global timestamp. Okay? Now, in order to be able to incorporate this information correctly in the constraints we have from the protocol we are using, IPv4, we have to change P4 program a little bit. I think, yeah, I will go over the rationale and then you can, should I go straight to the solution of this timestamp, or do you prefer to explain the rationale and maybe yourselves try to do it a bit? What do you prefer? Okay, straight to the solution. Okay, so just open here the timestamp int P4. It's under controller SRC tests, Hackfest 3, int solution timestamp int P4. Okay? Let me run just in the background to be able to showcase you a new deployment. Okay, so let's go over this P4 program I have given you. What we are changing now? First of all, here in the int header, in the previous one, in the int header, we had these three, where is it? Yeah, here. We had these three information. So switch ID, queue depth, and output port. And these are of type switch ID type, queue depth type, output port type. These three are defined here. So we have also, if you try and go into P4 programming, you will see a lot of times counting bits, because you have to count the exact packet header, and if you miss by 1 bit, this could lead to another packet parsed, etc. So counting bits is part of P4 writing. So here we have 13 plus 13, so 26 plus 6, 32. We will keep 32, and to accommodate the timestamp that it is 48, we will remove everything else. We will just have, where is it here? We will just have timestamp. So instead of these three, here we have just, okay, I should have changed the name here. Okay, disregard this. Timestamp T. So instead of queue depth, etc., here we have timestamp T. Basically, we're taking the whole space of 32 bits for timestamp. And also here, in the header, we don't have the 3 fields we had before, we just have timestamp. The rest of the changes are basically not that interesting. Basically, here, before, line 204. So before we had here putting in the int headers, the switch ID, the queue depth, and the output port with specific casts. Now in the new program, we have just timestamp, keeping only the 32 bits, so not the whole 48. Okay? So now, with this program, the rest is the same. We keep that. We also keep the switch ID, even though we don't do that anything, just to showcase you that it can be done. Okay? So let me just compile this, and I will show you what it will give us. Hackfest 3, int solution timestamp. Okay, it gave us a warning here that there is an unused parameter. We know that, it's what I said before. It's a warning, so the compilation went okay. We can, for the sake of this exercise, disregard it. Then we're going to go over our routine again to copy the artifact, the P4 artifact, bootstrap, and create service. And I don't have anything open, so and make CLI. Forgot something. If we take a look at the receive now, this is Scapy, so it's not really important, but when we are parsing the packet on the end host, we are parsing these 3 fields. This has changed now. So in case you use these scripts to build something else, make sure that if you use the receiver and the sender, this should be changed. Basically, the receiver should be changed. Okay. So let me just copy this in the correct place. sniffing. The sender is the same, it doesn't change. But now if we go here, you can see different timestamps. So we know from before that the stack goes that way. So this is the first switch, the second switch, and the third switch, if I remember correctly. And we can see that here it's, if we keep only this, here it says 20634, here it says 22949, and here 24022. So we have the timestamp of when the packet arrived on the switch. This is actually more useful because from that we can calculate the latency in each link, for example. And it is an interesting exercise if you want to get to Hanzetti. How we can take this, combined with what we did in the morning with the monitoring, and actually send this stuff, instead of the ping we did from end to end, send this stuff to monitoring, and have policies with that stuff. It is a little more complex, but it can be done based on the scripts that we have seen today. So I think that you can understand the, let's say, the power of in-band telemetry and how it can be useful in the sense that we now can have, we could always had. I mean, there were in-band telemetry protocols that were defined before P4. The difference is that with P4, it gives you the kind of abstractions to write your own custom protocols and to be able to tailor-made, to create a tailor-made solution for your specific needs. Okay? Also, the fact that before P4, if you needed some other protocol to be, or some specific function of a protocol to be implemented on your switches, for example, if you had this switch from vendor A, you should contact vendor A and say, okay, I want you to support this option or support this protocol, and he would have to create a new firmware and burn the firmware in the device, etc. Here, the power of P4 is exactly that. We can control our switches. We can create protocols for switches, and we can create custom solutions. For me personally, I see P4 like high-level languages. How we went from assembly to high-level languages, and that allowed us to build powerful software. For me, the paradigm shift is more or less the same. We go from static protocols to things that we can define ourselves, and we can program, essentially program the whole network by ourselves. Of course, as we have discussed before, this creates a really high ceiling on what we can do. So it needs some elaboration and thinking on how we can actually reap the rewards, the powerful abstractions P4 gives us. This is just a taste of what we can do. It's not much. It's just a simple taste of that. So, yes, here I have what actually I told before, that you could actually use KPIs from here from in-band telemetry and use them as KPIs with monitoring. There is the in-band telemetry specification from the P4 working group that has a lot of information on in-band telemetry, how it can be applied, etc. The next presentation will be by me and not Georgios Katsikas, because he's in plenary doing another presentation. We'll go over this more theoretical stuff from the in-band telemetry. And also, of course, if you need anything, either in P4 or regarding Hackfest or regarding Teraflow, do not hesitate to contact everyone in Slack, in the Teraflow Slack. And also, this is my mail. Feel free to, to send me whatever you want. Okay. So, now we're going in the last presentation. Basically, the part of the Hackfest has ended, the hands-on experience. I hope that even though we had problems and errors come up, you grasped some ideas of Teraflow and you saw some parts of it. So let's go on the last part, and then we'll close maybe a little earlier than expected. Okay. So the last part is regarding the future work. Basically, what we want to support for P4, and a call to action for anyone that actually wants to get involved and collaborate with us to build that. So we were going to start with the introduction to in-band network telemetry. We already show some examples, but as I've said before, these were primitive and not really in-band telemetry because we had the sender and receiver on the two hosts. We're going to show the three different approaches that exist based on the in-band telemetry specification. And then we're going to close with what we perceive as the required extensions for HCTFS, for the Teraflow SDN, to support in-band telemetry. So, what is in-band network telemetry? I think that I've spoken enough about this. So I'm going to go over the approaches. So basically we have three approaches. The first one, it's called export data, or int XD for short. Basically, what that means is that someone has already entered some specific, what are called postcards, basically some configurations in the header, and then the switches, one by one, when such a packet arrives, they read that they read that instruction and report to the controller what the instruction says. So you can think about this as just read. The second is embed instructions. Here, only the instructions are embedded in the packet. Sorry? Yes. So here, it looks like the first one, but the difference is that the packet can be modified a little. So what that means is that here we can, the switch can write, but it can write only regarding the instructions. So it can request from the next switch to also report that. So in the first case, we report only what the first one said. In the second one, we can change a bit the instructions. And on the third, we also embed data. We also put the data, instead of reporting it to the controller, we also put it in encapsulate it in the packet. We will go over this one by one. So first of all, some terminology. So we have this, which is called int domain. It's what I've said in the before lunch, that we have a specific domain where we're using in-band telemetry. So we could say that this could be the whole network, but this could not be realistic, and maybe we want just a little part of our network to be to have telemetry. Also, we can have different domains. So, for example, here could be a domain, and then there could be another domain. And for some reason, we want this to be separate. So an int domain is a series of nodes that we want for that part of the network to have in-band telemetry. Okay? Here we have the flow watch list, which is basically are rules set by the controller that define what kind of instructions, int instructions we have. So what kind of metadata, what kind of header fields we want to extract. Here we have the two differences. This kind of metadata can be written as rules by the controller, or can be written as part of the packet. These are the difference between before we had three different cases. This is the difference between the first two. Basically, the first one is predetermined instructions from the controller on what to report for each packet. Here we have the instruction embedded on the packet. So this is a little more flexible. We also have a source node, which is, let's say, the ingress node of our in domain. And we also have an sink or egress node. These are the two boundaries of our in domain. And in the middle, we have all these transit hops, which basically are collecting the various metadata. These three roles, based on what model of in-band telemetry we use, have different things to do. So now we're going to go over this. Yes. So in the first case, in the XD case, there is a controller that sets some specific watch list on the switches. So what kind of information I want from the switches to send to me. Okay? Here, all the switches have the same roles. So there's no differences between ingress, egress, or hop. All the switches report to the controller, to the monitor, the same exact information. So when a packet comes here, the switch takes some metadata and reports it to the monitor, basically the controller. Then when the packet arrives at switch B, the same happens. And then at C, the same. Okay? So these are predetermined. In the packet, there is nothing, there is no instruction on what should be reported. We just predetermine by the controller that whenever you have a packet coming, we want to get that information. This is not really, it's not really in-band telemetry because we could do that with regular switches too. And of course, there are no packet notifications. In the MX embedded instruction case, we have a flow watch list only on switch A. So basically, we say to the source, to the ingress, what kind of metadata we want to propagate to the rest. And what that does is that when a packet comes, first of all, it reports what it needs to report, like in the previous case, but also it enters the instructions in the header. So the second one receives the instructions from the one before, reports, and forwards. And the same happens with the third. Also, the third one, the egress, strips these instructions. So here we have separate roles for the ingress and egress, and the hop just forwards and sends the in-band telemetry. In the third one, which is the embedded data, again, we have a controller setting a flow watch list on switch A. However, now, switch A, when a packet comes, it does not report directly to the controller. Instead, it enters the information in the packet itself. This is what we done, not fully, but it was towards this case. Then this is forwarded to the second one. Each transit hop enters some more information. And finally, on the sink, all this information is sent to the monitor. Okay? So this has the least communication to the monitor, to the controller, but has the more payload, let's say. The packets, as they go through the switch, they are becoming bigger and bigger. So it is a matter of trade-offs.